Yeah, let me remind you of the definition of continuity of a function from one matrix space to the other. Yeah, we have two matrix spaces, xd1 and yd2. And we have a function f from the first matrix space to the second matrix space. And we also have a fixed point x naught on the first matrix space. Then we say that the function f is continuous at the fixed point x naught on the first matrix space x if the following epsilon delta technique is true. Yeah, no matter what positive number epsilon you choose, depending on that, there exists some other positive number delta of epsilon such that if you take any point x in the delta neighborhood around x naught, then the corresponding function values of f, the corresponding function value of f at x is sitting inside the epsilon neighborhood around f of x naught. Yeah, that's the formal definition. That's the formal definition of the continuity of the function f at a fixed point x naught on the first matrix space x. Then how do we write this expression over here? X is on the open ball around x naught. Okay, x is in the delta epsilon. excuse me. X is in the delta epsilon neighborhood around x naught in the first matrix space x with matrix D1. So how did we write this expression equivalently? That expression is equivalent to what? D1 metric, the distance D1 between x and x naught is less than delta of epsilon. That's what that means, equivalently. Then how do we write this? Another expression over here, the other expression over here. F of x is in the epsilon neighborhood around the f of x naught. Then that must be equivalently what? That is happened on the matrix space Y with the D2 metric, right? So that's the equivalently what? D2, the D2 distance between f of x and f of x naught is less than epsilon equivalently. That's what that means. Yeah, here is the first matrix space X with D1 metric. And there is another matrix space Y with D2 metric. And then we have a function f from the first matrix X to the second matrix space Y. And then we have a fixed point X naught on the first matrix space X. And then we say that the function f is continuous at that fixed point X naught on the first matrix space if no matter what epsilon neighborhood around f of x naught we have chosen, yeah, no matter what epsilon neighborhood around f of x naught we have chosen, depending on that, there is some delta of epsilon neighborhood around x naught such that if you take any point x wherever inside that delta epsilon neighborhood around x naught, in other words, that if the distance between x and x naught is less than delta, that's what that means, then the corresponding f function values at the point x must be sitting somewhere inside the epsilon neighborhood around the f of x naught. In other words, the D2 distance between f of x and f of x naught is less than epsilon. That's the rough geometric picture to explain the continuity of the function f at a fixed point x not on the first metric space x. If this has happened everywhere on the whole metric space x, we say that the function f is continuous on the whole metric space x. So we say that the function f is continuous on the whole metric space x if the function f is continuous at every point x not on the first metric space x. Well, you already recognized, right? If both x and y are the whole real number line and both D1 and D2 matrix are absolute value matrix, then what? This definition goes back to what? Exactly what? The continuity of what? The real value of the real valued functions with absolute matrix we have studied in the real analysis last year, right? And then both D1 and D2 matrix here are replaced by what? Absolute values, right? So this is the generalization of the continuity to what? General metric spaces. Okay. And then we can easily justify the following theorem. Yeah, we have two metric spaces, x and y. Then the following statements are equivalent to each other. The following four statements are equivalent to each other. The first statement is the function f. Yes. Okay. And we have a function f from the first metric space x to the second metric space y. And then the following four statements here are equivalent to each other. The first one is the function f is continuous on the whole first metric space x, which means the function f is continuous at every point x not on the first metric space x. That's what that means. The second statement is the sequential criterion for the continuity you have already studied in the real analysis on the real number line. That will be, naturally generalized to the general metric spaces here. If you take any sequence x of n, okay, in the first metric space x such that the sequence x of n converges to x on the first matrix space x, then the corresponding f valued sequence f of x then converges to the corresponding f value at the point x in y metric space. Yeah, that was exactly the sequential criterion for the continuity we have used in the real analysis on the real number line, right? And then that's naturally generalized to what? The general metric space theory. Okay? Yeah. So, and those two statements are equivalent to each other. Okay? Continuity is equivalent to the sequential criterion. Okay? Yeah. If you take any sequence converging to some point x, if you take any sequence x of n's converging to x, okay, And then its function valued sequence, f of x of n must be converging to what? F of x. That's what that is about. That's exactly the sequential criterion for continuity. If you choose any sequence x of n converging to the point x, then its function valued sequence f of x of n must be converging to what? Function value of f at x, which is f of x there. That's exactly the sequential criterion for the continuity we have already experienced in the real analysis. Okay? For the real value of the functions with absolute value matching. And number 3. If you take any open set U on the second metric space Y, then the inverse image, that's not an inverse function. We don't guarantee the existence of the inverse function of f, right? Because we don't guarantee the function f is bijective, one-to-one and onto, right? So that's not the notation for the inverse function of f. That's the notation for what? Inverse image of f. If you take any open set U on the second metric space Y, and then the inverse image of that continuous function f on U is also open. Oh yeah, then I have to be more precise. Yeah, if you take any open set U on the second metric space Y, okay, in the second metric space Y, then the inverse image of f on U, you take an open set on the second metric space Y and take its inverse image of f, then what? That inverse image of f on U will be some subset in the first metric space X. Then that inverse image of f on U will be also an open subset on the first metric space X. That's another equivalent statement for the continuity of the function f on the whole metric space X. Okay? Which means the inverse image of the continuous function preserves openness. That's what that means. If you take any open set on the second metric space, then in the inverse image of f on that U, the subset U is what? Still open on the first metric space X. That means inverse image of continuous function preserves openness. Okay, openness, that's what that means. The same thing is happened on the closed subset. Okay, the same thing is happened on the closed subset. Yeah, let's go back to our picture there. Yeah, if you have a continuous function f from the first metric space to the second metric space, then what? Okay? Then equivalently, if you take any open set U, okay, on the second metric space Y, then its inverse image by the continuous function f, its inverse image by the continuous function f will be another open set on the first metric space X. That's what that means. Which exactly means the inverse image of a continuous function preserves openness. The same thing has happened for what? A closed set. That will be the last equivalent statement of that theorem. If you take any closed set, E, if you take any closed set E, on the second metric space Y. Then the inverse image of F on E. The inverse image of F on E. Inverse image of F on E must be also open. Oh, sorry, must be also closed. In the first metric space X, which means what? Inverse image preserves closedness as well. Okay, closedness as well. Yeah. And all those four statements are equivalent to each other. So on the real analysis for the real variable functions, last year, number 3 and number 4 were what? Called global continuity, the global continuity in the absolute metric, absolute valued metrics in the real analysis, right? Yeah. And then I will leave its proof as homework question. Okay, yeah, you can easily try to prove the equivalency of those four statements, as you have already experienced on the real analysis last year, right? So I will leave its proof as homework assignment for you. I believe it's time to define the continuity on the more general topological space. You know, I use this picture many times in this class. The whole real number line with absolute valued metric is a special case of the n-dimensional Euclidean space with distance metric on, right? And n-dimensional Euclidean space is a special case of what? Metric space. Okay, metric space. X with distance metric d on it. And distance, the metric space is a special case of what? Topological space. With collection of called what? Open subsets of the topological space X, right? So every subset in this collection, tau collection is what? Is called an open set on that topological space. Where we have defined the continuity of a function on the metric space here, on the definition. So that covers the definition of a continuity on every metric space, right? Then how do we define the metric, the continuity of a function on the more general topological space, which doesn't have the metric on at all, right? The general metric space may not have a metric on. The general metric space may not have D1, D2 metric like those, right? Then how do we define the continuity of a function on the general metric space without having metrics on? We want to use the number 3 as the definition of the continuity of the general metric space here. Even if the general topological space may not have metric on, the general topological space still has what? Open and closed sets. Open and closed sets. So let's use this number 3 here as the definition of continuity on this general topological space. Okay? So more precisely, the global continuity theorem we have studied in the last year for the real analysis will be used to define the continuity on this general topological space. That's what I mean. Okay? That's what I mean. So here is the definition of the continuity on the general topological space. Okay? we have two topological spaces, X tau1 topology and Y tau2 topology. Both of them are topological spaces. And we have a function f from the first topological space to the second. And then we say that, then more precisely, we have a function f from the first topological space x with tau1 topology on to y with tau2 topology on, right? Yeah. Then we say that the function f is continuous on the first topological space x if its inverse image preserves the openness. Okay? If inverse image of f preserves the openness. Equivalently, how do we write this out equivalently? If you take any open set U on the second topological space Y. Yeah, what does that mean? U is an open set on the second topological space Y. What does that mean? That means the opening, the subset U is an element in the tau2 topology. That's what that means, right? Yeah. You know that every, subset of Y in tau2 topology is called an open set in tau2 topology, in the second topology on Y. Then, its inverse image, F inverse on U, on the first topological space X is also open. In other words, inverse image of F on U is an element in tau1 collection. That's what that means. That's what that means. Yeah, this is the formal definition of the continuity of the function f from one topological space to the other. Okay? That exactly means the inverse image of f preserves the openness. That's what that means. Then we say that the function f is continuous from the first topological space to the second. You already know that what? If we have two continuous functions and then their composition is also, right? That's what I will describe on this note here. We have three metric spaces. And suppose the first function f is continuous from the first to the second metric spaces. And the second function g is continuous from the second to the third metric spaces. Yeah, both f and g are continuous. The first function f is continuous on the first metric space X, and the second function g is continuous on the second metric space Y. Then you know the conclusion of this note. If you have two continuous functions and then their composition is also continuous. Yeah, the composition of f and g is also continuous on the first metric space X. Actually, f is from X to Y and g is from Y to Z. So the composition of f and g will be from the first metric space X to the third metric space Z, right? Yeah, here is the first metric space X with D1 metric. And there is the second metric space Y with D2 metric. And here is the last metric space Z with D3 metric. And the first function f is continuous from the first metric space X to the second metric space. And the second function g is also continuous from the second metric space Y to the last metric space Z. And then the result of that note says what? The composition of two continuous functions f and g is also continuous from the first metric space here to the last metric space there. That's what the result of that note. Now that's pretty easy. We can easily what? Justify, okay, the continuity of the composition of two continuous functions by number 3 on this theorem here. Let's take any open set in the last metric space Z and then see what happens to the inverse image of f composition G on that open set U we have chosen. Right? Yeah, that's what we want to see. For the proof for the justification of that note, let's let U be an open set on the last metric space Z. So let's take an open set U on the last metric space Z, and then what happens to the inverse image of f composition G on the open set U we have chosen on the last metric space Z? How did we write this inverse image of this composition on U? That is same as G function value at that's same as inverse image of f at inverse image of G on U. That's how we rewrite the inverse image of f composition G on U, right? You know. We go f first and then G afterwards, right? In the forward direction. How do we go backwards direction? How do we go backwards for the inverse image? To take the inverse image of f composition G, we must what? Take the inverse image of G first, and then we take the inverse image of f afterwards, right? That's what it is about. We go backwards direction for the inverse image. So this equality is true. The inverse image of f composition G is same as what? G on U is same as, we take an open set U here on the last metric space Z, and then to take the inverse image of f composition G, to go backwards from here to there, we must take the inverse image of G on U first. And then we take another inverse image of f on g of u afterwards. So that's the inverse image of f on g of u subset. That's what must be happening. Then that will be the inverse image of f composition g on u. That will be the inverse image of f composition g on the original open subset u on the last metric space z. But then I believe that's almost all, right? Because g is continuous and u is open. Because g is continuous and u is open by the theorem number 3, right? G inverse image of g on u is also open. And that's true since g is continuous and u is open. And then how about the whole? Yeah, this is an open set. So what happens to the inverse image of f on that open set? Because f is also continuous. Okay, because f is also continuous. Because f is also continuous and g on u, okay, g inverse image on u is open. So what? Its inverse image on f is also open, right? So this whole thing must be what? Also open since the first function f is continuous and the inverse image of g on u is open. Right? Because g is open and u is, because g is continuous and u is open, inverse image of g on u is open. Here it is. So this is open by the theorem number 3. And because f is open, and inverse image of g on u is open, sorry, I keep getting confused on my terminologies. Because f is continuous, and the inverse image of g on u is open, so inverse image of f on that open set, the inverse image of f on that open set must be also open by the theorem number 3 again. So we conclude the inverse image of f composition G on the open set U on the last metric space is open in the first metric space X. That's what we must conclude. So the inverse image of F composition G preserves the openness. That's what we must conclude. So by the theorem number 3 again, we must conclude what? The function F, the composition of F and G must be continuous. By the theorem number 3 here, we must conclude the composition of two continuous functions F and G is also continuous on the first metric space X, which was what we have desired. Any questions or any comments? Yeah, everything here, is a natural generalization of the stuff we have already studied in real analysis last year. Right? If we replace all metric spaces by the whole real number line R, and if we replace all metrics by absolute valued metrics, then every result is reduced to the results we have already studied in real analysis last year. Yeah, right? Yeah. Any questions or any comments? All right then. Yeah, let me state a lemma. I believe you still remember a Lipschitz function we have studied in real analysis last year. So then let's generalize the Lipschitz function to the general metric space here. Okay, that's what the lemma is about. Now suppose we have two metric spaces, x d1 and y d2. Yeah, both of them are metric spaces. And we have a function f from the first metric space x to the second. And there is some positive constant c such that d2 distance between f of x of 1 and f of x of 2 is less than or equal to that positive constant c times d1 metric, d1 distance between x of 1 and x of 2. For all x of 1 and x of 2 on the first metric space x. No matter what x of 1 and x of 2 on the first metric space x we choose, d2 distance between their f function values is less than or equal to that fixed positive constant c times d1 distance between the original elements x of 1 and x of 2. What does that mean? That immediately means what? That immediately reminds you of what? The Lipschitz function we have studied in the real analysis last year. If we replace both d1 and d2 by absolute values, right? Then that's what's happened. That was exactly what the definition of Lipschitz function we have studied in the last year in the real analysis. Then what is the result? What is the conclusion of this lemma? If this inequality is true for every point x1 and x2 in the first metric space x, then there is no other choice for the function f. F must be a continuous function. The whole metric space x. For its simple justification, simple proof, let's use the sequential criterion for the continuity. Yeah, the sequential criterion for the continuity is equivalent to the continuity of the function f, right? So suppose x of n is a sequence converging to x on the first metric space x. Okay, which means both sequential terms x of n and x are elements in the first metric space x. That's what that means. Then we can immediately apply this inequality condition to the sequential sets and the point x the sequence converges to. Then the inequality assumption says D2 distance between f of x of n and f of x is less than or equal to that fixed positive constant times D1 distance between x of n and x, which is true for all natural number index n. But because the sequence x of n converges to x, the D1 distance between x of n and x is converging to 0, right? And then what must be happened to the smaller one? Actually, the D2 metric between those 2 points is anyway some non-negative numbers. And the left-hand side, that's also a sequence on the real number line, right? 0, 0, 0, 0 sequence converging to itself. And on the right-hand side over there is another sequence converging to 0 as well, right? So what must be happened to what? The squeezed sequence in the middle. We may apply the squeeze theorem, right? Because all 3 spots, here, here, there are what? Real sequences on the real number line. So we can apply the squeeze theorem we have studied in the last year in the real analysis. Because the sequence x of n converges to x. Because the sequence x of n converges to x. D1 metric between x of n and x is converging to 0. So this right side real sequence is converging to 0. Yeah, this is a real sequence. D1 metric value between x of n and x. That's a real sequence. The real sequence on the right-hand side is converging to 0, and the constant sequence on the left side over here is converging to itself, 0 as well. And so, by the squeeze theorem, the squeeze sequence in the middle must be converging to 0 as well. So D2 distance between f of x of n and f of x must be converging to 0 as well. And so what? And so equivalently, what do we conclude? F of x of n, this sequence must be converging to the number f of x. That's what we must conclude, equivalently. So no matter what sequence converging to x we choose on the first metric space x, that's an arbitrary sequence converging to x on the metric space x, first metric space x, is function valued sequence f of x and converges to the function value of f at x. So we conclude what? By the theorem. Theorem number 2, I think, the sequential criterion for the continuity. We must conclude the function f is continuous on the whole metric space x. So every Lipschitz function is continuous. That's what that means. That's what the lemma means. Every Lipschitz function is continuous. Okay, then for the last 1 or 2 minutes, then let me describe the definition of homeomorphism. Homeomorphism. Have you ever experienced on homeomorphism? What is the definition of a homeomorphism between 2 metric spaces? in the more general sense. We have two. What is the definition of the homeomorphism between two topological spaces? So let's let x tau 1 and y tau 2 be topological spaces. Then we say that a function f from the first topological space to the second topological space is a homeomorphism. That's a new terminology we have not experienced on the real analysis last year, right? We say that a function f from the first topological space to the second topological space is a homeomorphism if, first of all, the function f is bijective, which means 1 to 1 and on to. And secondly, the function f must be continuous. Which means its inverse image preserves openness. And furthermore, the inverse function, that's not inverse image. Because f is bijective, we guarantee the existence of its inverse function. And that's not the notation for inverse image. That's the notation for what? Inverse function. I'm sorry for the confusion, but because, yeah. Inverse function of f is also continuous. We say that a function f from the first topological space to the second topological space is a homeomorphism if the function f is bijective, 1 to 1 and on to, and if the function f, the original function f and its inverse function, both of them are continuous. Then we say that two topological spaces are homeomorphic. Okay, homeomorphic. Homeomorphic if there is a homeomorphism f from the first topological space to the second topological space. Yeah, that's the definition of homeomorphism and homeomorphic. If there is some homeomorphism function between those two topological spaces, then when we say that those two topological spaces are homeomorphic each other. That's the definition of homeomorphism and homeomorphic between two topological spaces. And then, we will continue the properties of that homeomorphism and homeomorphic next week.